Welcome to Concrete Technology, Module 3, Lecture 1. In Module 3, we shall be looking into admixtures in concrete. First lecture, we will look into chemical admixtures, and the second lecture also will look into chemical admixtures, and the subsequent lectures will be on mineral admixtures. Recall that we are talking about concrete being 6 components, which include cement, water, fine aggregate, coarse aggregate, and other 2 are the 2 different types of admixtures, that is chemical admixtures and mineral admixtures. So, these are must in modern engineered concrete. You cannot think of a modern engineered concrete, which is without chemical admixtures or mineral admixtures. So, let us look into module 3 lecture 1. Our discussions today will follow. First, we will look into role of chemical admixtures, and largely we will be concentrating ourselves on water reducing agents today, which are called plasticizers, superplasticizers and hyperplasticizers. The nomenclatures of course vary. Some cases people call them plasticizers, superplasticizers and hyperplasticizers. Some other people call them as water reducing agent, high range water reducing agent and very high range water reducing agent. So, our discussion should be focused towards that today, right. But before that, we must look into the definition of admixture. Admixtures are chemicals added to concrete during the time of its production, right, during the time of its production, or it is also added to mortar or grout essentially at the time of mixing to modify properties either in wet state or after the mix has hardened. So, admixtures are essentially added to the conventional concrete, I will say, which are cement, water, fine aggregate and coarse aggregate, to modify the property as we desire. The property can be properties during the setting stage or in fresh state or after it has hardened. Can be a single chemical or number of chemicals, can be a single chemicals or number of chemical, right. It can be a single chemical or mixture of number of chemicals. So, generally in solution form, typically 30 to 35% would be solid active chemicals and rest all are solvent. So, it is in solution form, typically 35 to 40% active chemicals, rest all are solvent, and generally amount added is very small. That is why amount added is very small, less than 5%, quite often less than 2%. So, generally less than 5%, quite often it is less than 2%. So, that is why you call them as admixture. Now, historically if you see it, the plasticizers or water reducing agents, as we shall be seeing them, they came in 1932, and more effective plasticizers which are called superplasticizer, they came in 1963, Air entraining agent is an admixture which is used for in cold countries, mostly in cold countries, came in 1940s, and very high range water reducing agents came in 1980s and 90s. So, plasticizer 1932, air entraining agent 1941, super plasticizer 1963, and these are very highly effective high range water reducing agent polycarboxylate ether, they came in 1990 to 1999. Now, although it came quite early, their usage, they were not so popular in the beginning. So, practically they started becoming popular much later, perhaps in 60s, 70s, and if you see country like India, it is in 1990s in large infrastructure, but most of the concrete today manufactured in India or possibly many other developing countries of like ours, large quantity of admixtures are not used in non-mechanized concrete. So, in India large quantity of concrete is not mechanized, and there hardly any admixture is used. Okay. So, that is the history of their use, but we classify these admixtures depending upon their action. For example, those who chemically interact during the hydration process, their essential purpose would be to accelerate the setting or hardening process or both, and retarders are the ones which actually reduces down the pace of hydration, therefore, retards the setting process. So, retarders and accelerators, they actually interact during the hydration period, and they cause either acceleration of the hydration process, some cause retardation of the hydration process. Plasticizer are and super plasticizer I was just mentioning, these are adsorbed, they get adsorbed on the cement surface and they cause better particle dispersion. So, in a way they are dispersant, particle dispersant, cement particle dispersant, causes dispersion of the cement particles, separate them out from one from if it was the original situation, plasticizer will separate them out. So, that is what particle dispersant are. So, second class, they get adsorbed on the surface and disperses the particles. So, plasticizer, super plasticizer, hyper plasticizer, they belong to this group. Air entraining agent, essentially physically they allow air to be entrained into the concrete, but the effect is their action is they change the surface tension properties of water. So, they affect the surface tension properties of water, because bubble formation, air bubble formation is dependent on the surface tension properties of the air, and I mean liquid, because it is a liquid air interface. So, surface tension, if you want to make the water to entrap or entrain more air, then surface tension properties of the water has to be modified, and that is what the air entraining agent does. So, classification based on action is one that affects the surface tension. Actually, air entraining agent belongs to that category. Some can affect the rheology of concrete. For example, viscosity modifier. Viscosity modifier affects the rheology of concrete, that is change the viscosity at the plastic stage, during the plastic stage, and largely used in self compacting concrete or even in underwater concreting, one can use those. They are similar to anti-washout admixtures. So, they actually affect the rheology of water, viscosity property of water. They can modify the viscosity of water. In other words, it can thicken the water. We will look into that when we will discuss in details. Then there are special chemicals. They act on hardened concrete like corrosion inhibitors and water repellent. Corrosion inhibitors, water repellent, etc. So, this is the classification based on their action, but simultaneous classification or simultaneous name is also given side by side. They can be classified as accelerator retarders, plasticizers, superplasticizers, then air entraining agent, viscosity modifier, corrosion inhibitors and water repellent. And based on their action, this classification is actually based on their action. Accelerator and retarder interacts during hydration process. Plasticizer and superplasticizer actually get adsorbed onto the surface of the particle and cause particle dispersion. Air entraining agent modifies the surface tension properties of the water. Viscosity modifier will modify the viscosity of the water, so change the rheological properties. Corrosion inhibitors would of course stop the corrosion process, the electrochemical reaction, somewhere it will stop either anodically or cathodically. So, this is the classification of admixtures, but first we will concentrate on dispersing admixtures, that is the plasticizer, superplasticizer, etc. 60% of the admixture used worldwide are dispersing admixtures. The name plasticizer, superplasticizer and hyperplasticizer, etc. So, most of the admixture used in concrete belong to this category, that is dispersing admixture. So, first one is the plasticizer. As we said, that came pretty early, and this can reduce actually water. They plasticize the concrete. So, they essentially reduce the water demand in concrete. You can make it plastic with less water, that is the idea. So, they plasticize the concrete. So, if you add them into the concrete, they will make it more plastic, more flowable. Therefore, for same plasticity you can reduce down the water required. So, plasticizer, if you add them, they improve the plasticity of concrete, make them more plastic, and therefore, they are water reducing as well for the same kind of plasticity or cohesiveness or similar sort of, rather plasticity is the terminology I will use. For same kind of fresh concrete property, they can reduce the water. Therefore, we call them as water reducing agent as well. So, water essentially nomenclature differs. In STM classification, largely they will call them as water reducing agent, whereas some other nomenclature they will be called as plasticizer. Now, these plasticizers can reduce water requirement by 12% to 5%. So, it will be more than 5%, less than 12%. So, water quantity for same effect, plasticizing effect, it will reduce the water by this amount. The dosage generally, the amount you add is only 0.2 to 0.6% of the cement, or that is on cement. So, if you have 300 kg of cement, so 0.2% of that would be 0.6 kg in a meter cube. So, you see 0.2% to 0.6%. So, it will be about 1.8 kg. You see 3 kg is 1%, 0.3 is 0.1%. So, this is 0.2 to 0.6%, right. So, this much you will be adding in 1 meter cube of concrete. You can see that quantity is very small. This quantity is very small. This quantity is very small. So, dosage is low, 0.2 to 0.6%, and the material that has been used are lignosulfonate. Lignosulfonates are natural polymer from wood that is obtained after removal of sugar and carbohydrates, various carbohydrates. So, that is and then sulfonated. We will come to this process anyway a little bit more. So, lignosulfonates are the natural polymers that is obtained from wood, the source is wood. Then there are others like polycarboxylate ether based plasticizer. So, there the plasticizer could be either polycarboxylate or lignosulfonate. We will discuss this the chemistry a little bit more. Their use is usually for low to medium slump concrete. Now, slump is a terminology we have not introduced to you at the moment. It is a terminology related to moldability or working on fresh concrete. So, we will discuss this sometime later on. So, generally useful for low to moderate slump concrete, low to moderate slump concrete. Superplasticizer is the next variety. Superplasticizer is the next variety which reduces the water from 12% to about 30%. So, 12% to about 30% reduction. Water reduction is 12% to 30%, and dosage of course is now higher. So, it can cement takes more of it, more of this material it can absorb, because we said that they get absorbed at the surface of the particle, that is cement particle, and this they get more quantity can be absorbed on the surface of the cement particle, and dosage is usually 0.6 to 2% of the cement. So, that means if it was 300 kg of cement earlier, and maximum you would have added is 1.8 kg of plasticizer, but super plasticizer you might add from 1.8 to about 6 kg. So, that is the dosage is generally higher, but their action is also higher. Note that their action is also higher, they are more effective, and that is why the name, super plasticizer. You see, plasticizer, then super plasticizer. Well, the hyperplasticizer is also built in this. We have not made a separate list here, separate classification. So, super plasticizer or high range water reducing agent and very high range water reducing agent, that is hyperplasticizer, they are all included here. Now, they are synthetic and three types. First is sulfonated polymers of naphthalene formaldehyde condensate. So, sulfonated polymers of naphthalene formaldehyde condensate or sulfonated polymers of melamine formaldehyde condensate. There is a two varieties, second variety, right. So, they are sulfonated polymers of naphthalene formaldehyde condensates or melamine formaldehyde condensates, and third variety is polycarboxylic ether. So, these are the three varieties of super plasticizer, and that includes the hyperplasticizer as well. Chemically they are this kind. Now, if you look at the chemistry of the plasticizers, wood is made up of lignin and cellulose. Now, 20% lignin is present in wood, and of course, it has got variable structure depending upon the type of wood, the season it is taken from the wood, and so on and so forth. So, it has got a variable structure, and about 20% is present in the wood. Now, paper industry, they make pulp out of the wood. Paper industry make pulp out of the wood. So, in this pulping process, lignin is sulfonated. Now, what is sulfonation? This is treated with oleum, which is nothing but a solution of SO3 in concentrated sulfuric acid. In fact, you will write it as so. lignin is treated with this, lignin is treated with this, that is called sulfonation, that is called sulfonation. So, lignin is treated with this, it is sulfonated, that is treated with oleum to make it soluble, and then it is further hydrolyzed or fermented to remove carbohydrate. So, paper it is actually a product from paper industry. In the pulping process, lignin is sulfonated, it is treated with oleum in the process of sulfonation and then further hydrolyzed or fermented to remove carbohydrate. The key part in this one is in lignosulfonate, of course, phenyl propane units that can link up to form polymer. So, in this one chemically phenyl propane is a unit which can polymerize, and that polymer is a key part which is responsible for plasticizing effect, Now, the phenyl propane looks like this. This is phenyl with hydroxyl ion. So, this is phenyl and the SO3 sulfonated SO3, right, this is sulfonated, this is the simplified sulfonated phenyl propane units, and it has got a sodium SO3 with sodium, that is linked with sodium, you can see this, and this is the units, it get polymerized. So, this is essentially the structure of the phenyl propane unit, which is the chemical which is responsible for plasticizing effect. This structure is heavily cross linked. So, the polymer that is formed out of this is heavily cross linked, that means a cross link is, these are linear change. For example, there could be a linear another one, another of this molecule and another of this molecule, they will form chains, and when there are several chains which are cross linked in 3D, let us say 2D, 3D, that is cross linked. So, we say that cross linked, several such chains are connected in between, this is cross linked. So, the polymer structure is heavily cross linked and they form actually a spherical microgel like this. So, active microgel group. So, it forms a spherical microgel, right, it forms a spherical microgel like this, So, these are the active microgel groups, and you can see they are all linked up, cross linked in a 3D structure. So, it is almost like a heavily cross linked spherical microgel. So, that is what this structure forms, and its molecular weight, of course, if you look at it, varies from 2000 to 60,000, 2000 to 60,000, right, 2000 to 60,000, that is the molecular weight in normal carbon 12 scale. And in the solution, what happens is the active sulfonate group dissociate to SO3, there is something more on this side, and SO3 which will be negative, plus the sodium. So, sodium plus separates out, sodium ion separates out, leaving this portion negatively charged. Therefore, microgel which is there in the microgel structure of the phenyl propane, and it leaves it with negative charge. Now, this negatively charged molecule with each other, and if they are all negatively charged molecule, they will push the particle apart. So, that is the whole idea. The mechanism, of course, we will understand better. So, it is the negatively charged. Now, this negative charge ensure its attachment to the cement particle as well, because SO3 sodium dissociates, leaves with SO3 and negative charge, this can get attached to the cement particle, and induce a kind of negative charge onto the cement particle itself, and thereby cause dispersion. So, we will look into this slightly more in details as we follow through. The second one is superplasticizer, which is sulfonated naphthalene formaldehyde condensate, and we call it SNF. So, this sulfonated naphthalene formaldehyde condensates or polynaphthalene sulfonate is, this is also another nomenclature is there, polynaphthalene sulfonate, PNS. More commonly used is SNF, that is sulfonated naphthalene formaldehyde condensates. So, SNF, some people call it polynaphthalene sulfonate as well, PNS, and this is obtained by sulfonating petroleum or coal tar naphthalene at high temperature. So, you see this is also sulfonated in the same manner as the lignin, and this is done at high temperature. Naphthalene is now sulfonated at high temperature to obtain this material. The product is then polymerized with formaldehyde and neutralized with sodium, calcium or some other metal, I mean usually sodium and calcium salts, and molecular weight is small. That is why the quantity adsorbed onto the cement surface is more, more, and therefore, more possibly negative charge, therefore, more action compared to plasticizer. So, less molecular weight, more negative charge, because more it can be adsorbed onto the surface of the particle, more negative charge, and therefore, more dispersion. That is the idea, that is the idea, that is the idea. Let us see the chemical structure of it. Naphthalene structure is this is the naphthalene structure, and this is the sulfonated SO3 and the sodium with it, and then this is polymerized, n number of them, it will repeat, n number of them it will repeat. This is actually CH2, this is 2 has gone there, this is CH2, this is CH2, the 2 has gone there. So, that needs a small correction actually, this needs a small correction, the 2 has gone down, 2 is here actually. So, this CH2, right. So, this is the polymer. So, this is the naphthalene. Naphthalene is 2 benzene ring combined together, and in one of its arm would be SO3 Na, right, and this when polymerized, this is actually simplified formula shown, sulfonated polymer formaldehyde condensates, right, sulfonated naphthalene formaldehyde condensates polymer. So, simplified structure is shown, and this chain is linear. So, it is a linear chain will be formed, several of them linear chain will be formed, and it is free to rotate about formaldehyde derivative CH2, and SO3 Na group can be above or below. So, it is about in this axis it can rotate, and therefore, this can be above or below, this can be above or below, this can be above or below. Anyway, the main important issue is on dissociation, on dissolution, if you put in water, this component will dissociate into something, all other components SO3 with negative charge plus sodium positive charge, like the lignosulfonate, and this will now affect the dispersion in the same manner, because this being negative, it can get attached to the surface of the cement, which has got cationic surface charges, and there it can get attached and induce negative charge onto the cement particle itself. So, similar action as the lignosulfonate, only difference being more quantity can be absorbed, and its more action is more prominent. The next one is sulfonated melamine formaldehyde condensates, and this is similar as SNF, that is the earlier one that we looked at, sulfonated naphthalene formaldehyde, except that melamine ring replaces the naphthalene double ring. So, melamine ring will replace the naphthalene double ring. This is available only as sodium salts, not as calcium salts. Molecular weight is higher than SNF. So, slightly higher than SNF. and that is how it will look like. So, this is the naphthalene double ring replaced by melamine, which has got 3 nitrogen which has got 3 nitrogen in the ring instead of carbon. So, this is the melamine, everything else remains same, and here is your SO3Na, which is the main important component, and on addition to water this sodium will dissociate out, leaving everything else negative, which can get attached to the cement particle surface and cause dispersion. So, this is a simplified sulfonated melamine formaldehyde condensates polymer with n number degree of polymerization. So, that is showing the same. The last variety, that is polycarboxylate ethers. These are also called polycarboxylate, PC based polycarboxylate simply, or combed polymer. Carboxylates are nothing but derivatives from, they come from carboxylic acid having COOH group. This H gets replaced. In case of salt, this will be replaced by carboxylate salt, this will be replaced by metal, and in case of ether, in case of esters, they will be replaced by organic groups. Ethers are compounds which have got oxygen of this kind of structure, and let us see how do they look in our case. The backbone polymer is typically obtained from polymerization of acrylic acid, but can be substituted by other group. So, essentially carboxylic acid, carboxylates are obtained from carboxylic acids, which has got structure like this. So, typically they are obtained from acrylic acid, but you can substitute other groups. So, there is a lot of possibility actually, that is why many groups can act here, and this group is finally then neutralized by sodium that dissociate into solution. So, carboxylate group is neutralized by sodium, and in solution sodium gets separated out, leaving everything else negative, which can get attached to the cement particle. The chemical structure will look something like this. So, this is your COO, H is replaced by sodium, CH, and this is CH2, this should be CH2, 2 should go up here actually, this 2 should go up here, it has got some or other distorted, it has got distorted. 3 should be here rather than here, CH2 here, this has got distorted, and this has CH2, this is also CH2, etc., etc. So, this is not there, this is not there, all right, this got distorted. So, there is a polymer here, you can see this is CH2, CH2O, and that is ether, that is one ether. So, there is an ether here, this is the polycarboxylate, sodium carboxylate, maybe sodium whatever the so sodium is there in the acid, and in this one instead of sodium there is another ether polymer, copolymer. So, there is a copolymer here. So, there is a polymer here. So, you can see this is sodium, this will get dissociated, this will attach to the cement particle, this will attach to the cement particle, right, this will attach to the cement particle, but this one, this branches where there is a polymer, copolymer, this will remain outside, in the sense that this will remain attached to the branch. So, you have a comb structure, this is the branch which is attached to the cement, and something else is protruding out of it. So, this portion is protruding out of it, and this is the copolymer. More importantly, you can change this copolymer, it need not be CH2CH2O, ethylene glycol, as we shall see. So, the compound, you can have any polymer, copolymer here, ether copolymer, as any other ether here. So, therefore, you can, by changing this, you can actually tailor made the property of this plasticizer. Let us see how it is done. So, this is the basic structure of polycarboxylate ether, right. So, this the ether is here, and idea is like this. The copolymer here is polyethylene glycol CH2CH2ON. Other polymers can be used to tailor made the PC for desirable properties. So, this is the biggest advantage, and this development took place in 1990s, largely 1990s, let us say late 1980s and late 90s. So, therefore, you can see that there is we have a choice of actually designing various kind of or developing various kind of superplasticizer, or as they are called hyperplasticizer, using this polycarboxylate ether type of formulation. The polyether part is responsible for what is known as steric effect. I will come to steric effect, because it is now combed structure is combed. So, this is your main chain, which is the polycarboxylate chain, and here is the ether. So, the ether group chain is here polymer. So, therefore, this honeycomb structure, and this effectively increases the size of the particle, and causes further dispersion by size effect, which is known as steric effect. We will come to that sometime later on again. The sodium that dissociates provides attachment point for PC. So, PC gets attached to the cement, because sodium will dissociate, and that causes attachment to the PC. So, that is how the chemistry of plasticizer and superplasticizers are. Now, if you look into mechanisms of actions, we can now look into the mechanisms of actions, which more or less we understand from the chemistry. Basically, rheological properties of cement water paste is related to forces of attraction and repulsion, right. So, in the beginning, when you add water, the viscosity of that paste that you form, right, or its how much force is required to cause it to move or deform or yield, if I may say so. These are all function of the forces of attraction and repulsion with the cement particle themselves, right. So, two types of forces, of course, we recognize. One is the van der Waals forces, which are responsible for attractions. Van der Waals forces between the covalent compounds in the cement, as we have seen earlier when we looked into the chemistry of cement, they will cause attachment, or they will try to bring them together. So, they are attractive forces, whereas you see the free surface balances, they are essentially cationic in nature, because calcium ion, aluminum, they are there, and they are cationic in nature. That is why they can actually attach water also, get attached to the water to form water of crystallization, and the reaction, that is hydration, do takes place. So, they are positive in nature, and they cause repulsion of this particle. Now, the repulsion in the beginning is less compared to expansion. So, van der Waals forces dominates in normal cement paste, thus flocks are formed. So, in the beginning, if you do not add any plasticizer, cement tend to flock together because of this force. Although this force is there, these forces are more dominant, and therefore, flocks formation do occur, as it occurs in many other fine particle. But when you add this superplasticizer or water reducing agent, the superplasticizer get negatively, it forms negatively charged component, and then the metal ion, that is sodium or calcium that you have added, and this negatively charged component is attached to positively charged cationic surface, that they get adsorbed irreversibly. So, because of their negative charge and because the cationic surface characteristics of the surface, because of calcium, aluminum, etc., this negatively charged sulfonated compounds or negatively charged compound after dissociation of the metal gets attached to the cement particle, Now, they, since they are negatively charged, they now induce these negative charges into the cement particle itself, which can overcome the van der Waals forces, and therefore, deflocculation occurs or dispersion occurs. So, they induce negative charge on the particle after adsorption, and they cause dispersion. So, water reducers are surface acting agents, negatively charged as adsorbed on the cement particle or any other similar fine particle, giving particles negative charge, and this leads to repulsion. Leads to repulsion. Therefore, that is why they are dispersant. Now, negative charge also causes development of sheath of oriented water molecule around particles. That is, if this is your particle, now everything is negatively charged, and you know water is H2O is polar with this positive and negative charge not coinciding. So, therefore, water will get oriented, and it will give you a sheath of oriented water molecules for wetting purpose, and this results in release of some water. Some water gets released from restraining mechanism of flocculated system, and therefore, this water is available for more water is available for lubrication, therefore, the plasticizing effect. So, two ways: first it pushes, but this is possibly true for lignosulfonates, SNF and SMF. PC we will see on the other hand does something more. So, they essentially causes negative charge onto the particle, pushes them apart. Not only that, it creates a sheath of water molecule, oriented water molecule around the particle, and some water gets free, because now it is easily weighted because of the disciplined arrangement of the water, accumulation of water at the surface. Some water gets free, and that is how this water is available for further lubrication. So, they will look something like this, water reducing agent will look something like this, dispersing admixtures, cement flocks, and initially they were something like this, each of them were very close to each other. If you see, they were flocks, but now they got uniformly dispersed, increasing fluidity. So, this increases the fluidity. This is how they will look. The particles are, this may be your particles, this may be your particles. The chain, they are, if you, since SNFs are linear polymers, linear chain polymers, they are creating negative charges, and this negative charges repel each other. This is another particle. These are the, this is showing for SNF. You can see the naphthalene rings, double rings, naphthalene double rings. So, this is actually SNF action shown. So, SNFs are double rings here. So, this SNFs, and this is a polymer. So, long chain polymers with negative charge around, and this negative charge causing the pushing the particles apart, pushing this particle apart. So, that is how causing effective dispersion, Now, this charge increase has been measured also, and the potential, this charge increase is defined in terms of zeta potential. Zeta potential is the potential difference between the dispersion medium, that is your water, in our case it is water, and the stationary layer of fluid attached to the dispersed particle. So, if you have, these are your particle, and if your surrounding water layer is somewhere here, surrounding water layer is somewhere here, surrounding water layer is somewhere here, right. So, this water layer and potential of the bulk water here, this difference is called zeta potential. So, zeta potential is the delta V across the bulk dispersion and the one layer attached here. That is how, by definition, this is the zeta potential, and this zeta potential, if you measure, it is observed that as SNF dosage increases, zeta potential negative, remember this negative because potential is negative on the surface. So, minus 10 minus millivolt this is, which means this is plus 10 volt, plus 10, and these are all negative. Just for the sake of plotting we are showing it this way. So, as you increase the SNF doses, the zeta potential, which is negative zeta potential. So, negative zeta potential increases, but beyond a point of course, it does not increase further, which tells us that possibly there is an optimal dosage beyond which there is no further improvement by adding SNF. This may be, this is also true for SMF or possibly even lignosulfonates. So, negative potential has been confirmed by experimental studies through zeta potential studies, and that is what this diagram shows. If you look at very high range water reducing agent or PC based superplasticizer action. Now, you remember we said that this will have combed structure. So, there is another the copolymer ether. So, copolymer which is an ether, this will be here, this is the main carboxylate group. So, long chain, and these are the graft where you can put in any desirable ether depending upon the properties you require. And because of this, you find that a long chain outside, which are again polymers, this particle gets dispersed more. In fact, it is attached here because of the sodium dissociation. Sodium dissociation, it gets attached here, right. So, negatively charge the whole thing, and then the graft or the copolymer, that is the ether, is somewhere here, and that is what results in effective increase in effective size of the particle and pushes apart. So, this is called steric stabilization. So, therefore, the action of PC based admixtures are not the negative repulsion, rather largely it is the action of the copolymer which is grafted, and effective size increase. Because of the sheer size, they push each other apart and they are quite more effective. In any case, this is a negative charge, sheath of negative charge here as well at the surface. So, the steric effect is visual here. For example, you can see that main chain and the branches are here. So, main chain, the branches are on this side, these branches causes pushing apart. So, steric effect is because of the size. So, this is your cement particle, this is your cement particle, and because of the size they push each other more away from each other. So, push them away from each other, right. So, dispersing admixtures, continuing with that. Now, let us see some of their usage. How can you use them? We have understood the chemistry somewhat, and we have also tried to understand the mechanism of their action, right. Okay. Now, how do you use them? You can use them beneficially. In fact, in my opinion, or possibly opinion on most of the students of concrete and concrete technology, these are must, because these materials, I mean this admixture is a must in an engineered concrete, because it saves on cement. And if you remember, we talked about cement clinker is produced with the expense of energy, and it also produces carbon dioxide, greenhouse gas. And we also said sometime in the very beginning, then 1 ton of cement is equivalent to almost equivalent to 1 ton of carbon dioxide production. Cement in, I mean clinker, OPC clinker here. Now, if you can reduce your cement consumption, not only that you will make it cheaper, but you will possibly reduce, if you can reduce your clinker consumption, of course, you will reduce, you will help in reduction in greenhouse gas emission. Now, admixtures or plasticizers and superplasticizers have some sort of beneficial effect on these also. Let us see how they are. Consider a concrete with 28-day strength A and workability B, and I want to get a strength of 28-day greater than A, workability B. When we study further, we shall see that for doing that, what I need is to reduce the water to cement ratio, reduce. I want to keep the workability same, so largely the water I will keep same. If I keep the water same, right, and I want to reduce the water cement ratio, then I must increase the cement. So, I got to increase the cement. So, you want to go a concrete which has higher strength, which has got higher strength compared to this is A, this is greater than A, you would add cement. But same can be achieved through another route as well. We will come to that, but let us see in another case. I do not want to increase the strength, but I want to make it easily moldable. Workability is a terminology which is related to moldability. It should be ease of working onto it. In fact, in crude word I can say so. Now, you want to easily work onto it, you got to add water, right? You got to add water, because then it will be flowing and you can compact it easily. That is very common sense tells us. Its intricacy and details we will look into sometime later on, but at the moment we will assume that I have to add water. But then I want to keep the strength same, and I said that we will understand that strength is a function of water to cement ratio. Higher the water cement ratio, strength is lower. So, I have to maintain the water cement ratio. Therefore, I got to add both water as well as cement, because I got to maintain water cement ratio same as this. So, I got to I will add delta W, and proportionally I will have to add delta C such that W by C remains same. So, if this was the W by C, so this has to remain same here. So, I am adding water, adding cement as well. Here I did not want to increase the workability, but I want to increase the strength, therefore, I was adding cement alone. Now, same thing I can achieve by water reducing agent. What I do? I add water reducing agent, then I will reduce the water. So, if I reduce the water, keep the cement same, water cement ratio is reduced automatically. So, I am having delta W divided by C. So, water cement ratio is reduced, strength will be greater than A, workability will be equals to same as what it was earlier. So, using VHWRA I can achieve the same thing. Therefore, whichever route is cheaper, I will follow that. I will follow that whichever, perhaps this is cheaper route usually, because quantity added is very small. But the secondary benefit, you remember that you are all reducing the carbon dioxide emission as well. Want to keep the strength same and workability same, I will add some water reducing agent, reduce the water content, also reduce the C same. So, my W by C will remain same, and therefore, I will get the same strength. So, I get the same strength by adding water reducing agent and with lower cement content. So, again it might be cheaper route to add water reducing agent rather than add cement. So, you will have to see whichever is cheaper. And the last case, if I want to get this, I simply add water reducing agent, and this will ensure that I get higher workability, but same strength. So, you can see that by using water reducing agent, we can save on to cement. For same strength, if I add water reducing agent, I will reduce the water, I will reduce the water also correspondingly, cement also correspondingly. Therefore, there is a saving in cement, and this might be a cheaper route. Similarly, if I want to increase the strength, use water reducing agent, water will reduce, but cement will remain same. Therefore, strength may increase. And if I want to simply increase the moldability, I add water reducing agent without adding cement, but otherwise I would have had to add water as well as cement. So, this is how we can use. In the next class, we will look into this again. some more issues related to this we will see. Same thing can be explained in different manner. For example, without plasticizer, water content is here, the workability is here. Now, you add plasticizer, then the or plasticizer or water reducing agent, just add them, it will be more flowing concrete. But if you reduce the water, use a lower quantity of water, you will get higher, same strength, you will get same workability. So, this will make higher strength concrete. So, you can increase the strength. We will repeat from this diagram in the next class. There are several other benefits and some effects we will study. So, we will now summarize what we have looked into. We have looked into water reducing agent and some of their aspect we have looked into. This we did not look into today. In the next class, we will look into this. We have studied today, in fact, what are the admixtures, how do we classify them, what are their purpose, we have defined them, followed by we looked into plasticizers and super plasticizer, tried to understand their chemistry, definition, some action, mechanism and how they are useful in concrete system. We will continue with the super plasticizer and hyper plasticizer and plasticizer a little bit, including their other effects, what happens to the strength, what happens to durability and so on and so forth. They reduce the water for same plasticity, but do they have any effect? Those aspects we will look into, then look into other admixtures, namely the accelerator, retarders, etc., etc. Thank you very much.